Okay, here we are on part 2. So hopefully the board is up close enough that you can see it. So I'm just going to give it a try from this side. I see a little glare there. Let me see if I can adjust that. Okay, I'll try to avoid writing right there. So there's definitely a glare, isn't there? Okay, I need a camera assistant. All right, let's go on. Property number 4. And on property number 4, I want you to draw the graceful curve F from A to B. And I'm going to discuss a special case where I'm looking at the area under the curve from A, where's my lower limit of integration, to, surprise, guess what I wrote under there? It's quite a shock. It is A. I'm going to investigate not the area from A to B, like I indicated that I might be doing, but I'm going to look at the area under the curve from A to itself. So here, instead of having a rectangle, I just have a line. Hopefully you can draw a straight line. And I want to know what the area is under that line. Well, a line has no width. It's not even a rectangle to state that we have any width to it. So therefore, it cannot have an area. So the area is 0. There is no area under the curve from A to A. It's a very popular question that you'll see on standardized tests. And it is always testing whether you understand that principle. So jot it down. Number 5, here we have an integral that we are looking at, and draw the graceful curve, we'll call it F, and the parameters A and B. And as we look at this one, the 5th principle, I want to know what happens when we add a third parameter in between A and B. I'll put it a little offside, it's not exactly in the middle. I'll put in parameter C. So we have at x equals A, C, and B indicated on the graph. So I want to establish the principle here that the area under the curve from A to B, that whole thing, is the same as looking at the area under the curve first from A to C. So I'll just stripe it the other way from A to C. And then I'm going to add to it the area under the curve from C to B. So that will be striped in the same way. So A to C and then C to B. So notice that those areas are identical. The area striped this way is the same as the area striped that way. So hopefully that makes sense. A to B, when C is in between A and B, this kind of division can be, we can divide the integral into 2 individual integrals that we add up. And we get it like this. So write the principle, the integral from A to B. Let's indicate A is less than C, which is less than B, which is indicating that C is in between the 2 for this principle to work. A to B equals the integral from A to C plus the integral from C to B. All right, principle number 6. See if that shows up. Principle number 6 does not show up, so let me scoot the camera down. All right, try that. All right, on this one, the final principle is we are going to take the graceful curve and the parameters A and B, and we're going to indicate to ourselves the relationship between the regular integral from A to B of f of x dx and this guy. The only difference here, I haven't written in these limits of integration, but I have moved the curve. And from your pre-calc days, you learned that when you take a constant and it hugs the x variable like this, and it will move it left or right in the opposite of what you might think. So a negative c is a right move, a right shift of this curve. So let's take your pencil and move this f curve c to the right. So I'm just going to pick a c And this mountain and this valley are going to move C to that direction. So I'll try to draw this. It's not too easy. So this mountain was here and now it's here. So I have shifted it to the right, C. So similarly, go ahead and shift your curve, C to the right. And now I want to find a way to make these areas equal. So right now, if I write, right now, are they equal as they stand? Is the area under the first curve, this area right here between A and B, like if I just put in A and B, don't write this, but let's just think about it, is that the same as the area under the shifted curve between A and B? Those two areas are not alike, so therefore there must be another limit of integration that I can put in here in order to show this scenario. It's going to be hard to uncover this. Alright, so here we have our curves back. What it is that can make these equal is if I can also shift this A over C and this B over C. So I'm going to shift that. Instead of A, it's going to be A plus C. Instead of B, it's going to be B plus C. So let's talk about that. So the area under the curve from A to B, we visualized. I'll just kind of dot it in. A regular area that we talk about so often. And now we're looking at the area between A plus C. So my C was about this much. So A plus C is about right there. And my B plus C is about right there. So let's look at the area under the curve from A plus C to B plus C. Can you see it's an exact replica of what I had dotted over here? It's just shifted over. So this principle is always true. In the integral from A to B of f of x dx is the same as the integral of f of x minus c, indicating a right shift from A plus c to B plus c. Same old integral, same area. All right. One more, it's not a principle, but one more thing that's going to show up in your assignments today. And let me check the time here. Alright, we're okay. I have time to show it to you. Alright, the last principle, and it is not one of the properties, but I want to prepare you for what's ahead. And that is, I want to show you the area that we can come up with, an integral, which has an exact number. And it looks like this. Suppose I ask you to find the area of the integral from minus 3 to positive 3 of the square root of 9 minus x squared dx. And we haven't taught you how to numerically do integrals unless you have a graph and set that long limit process. So without the long limit process, it'd be helpful if you could see what I wrote. There you go. Alright. Without the long limit process, and without teaching you numerically how to come up with this number, there's still a way for you to get the integral of this. And here's what it is. The trick is recognizing this function. y equals 9 minus x squared. If I move the x squared, the square root of 9 minus x squared. If I algebraically change this, it should be something that you recognize. So let's see. Square both sides. Move the x squared over. And I get x squared plus y squared equals 9. And that should be a familiar friend from pre-calc. And that is a circle with radius 3. So what this is asking you to do is look at this minus 3 plus 3, and there's a circle of radius 3, and it's at the origin, x squared plus y squared. It's centered at the origin with a radius of 3. Does that show up? Yeah, I'll just bend it down just to make sure. Alright, now we can come up with the integral, because the integral is the area under the curve. And because this is not minus, it's indicating it's just the positive square root. So we're really only looking for the part above the x-axis. But that's just the circle. What's the area of any circle with radius 3? Pi r squared, in this case pi 9, but we only want half of that circle. So 9/2 pi is the area under the curve, the integral from -3 to 3 of this expression. So don't let that one scare you off, because it's not scary at all. Alright, let's look at an example of what you'll be doing in your assignment for the rest of the period, and you carry it on into this evening if you need to. Alright. What we're going to do is discuss an example. Let me check the time. I better close this down. I'll put the example in the next part, and that'll be our final part for today. So, be right back.